Okay, is it going to work this time? All right, so we have problem number one, where we're talking about a continuous f and g and an h that are differentiable. And the idea is sort of a little twist in the fundamental theorem of calculus, which I have written over here. The regular fundamental theorem says that the derivative and the integral kind of cancel out, leaving you with just f of x. And the idea behind this problem is saying, well, okay, do we get the desired results of just sort of getting the chain rule to pop out, right? Because you see how we have, instead of x, we have h of x here and here. So then we kind of get the chain rule to pop out, right? So intuitively, this kind of makes sense, but the issue is you also have this other, I guess it should be a g, minus f times g of x times g prime. So this is what we want to show. Yes, this is what we want to show. This is what the problem gives us. So we kind of just have to figure out how to word it this way. And I think this should be reasonably clear. So one of the things is, okay, let's just rewrite it. So going from g of x to h of x. One of the things that's a little bit confusing is that in the fundamental theorem of calculus, this a is sort of a constant, whereas this x is your independent variable. Whereas here you sort of have both things that have the independent variable inside them. So what you just got to do here is you just got to split it up. Off the top of my head, I don't know if there's a theorem for this, but the idea is that you can sort of just split it up in the middle for some arbitrary a. And this is going to look like going from g of x to a f of t. Yeah, what this looks like is splitting it from, before you had the bounds of h of x and g of x, now you sort of split it in the middle with a. So what this looks like is if this function here was ft, what this is essentially saying is if this point was a and I don't know, some point over here was g of x for that some particular value of x, and this was h of x for some particular of x. I don't know, maybe call it like x naught. The idea is basically sort of saying the entire area under the curve is equal to this area plus this area, which makes perfect sense, right? It's sort of splitting the areas up and they add together pretty nicely. So with this in mind, you can always flip the sign of the integral by switching the bounds. So this turns into a minus a times g of x f of t dt just fine. Exactly as you would hope. F of t dt. By the way, I'm explaining this relatively simply and intuitively. If your textbook has some theorems to make these things rigorous, I don't, off the top of my head, I don't remember if there's a theorem justifying being able to flip the sign or being able to split the integrals apart, but always make sure to use the appropriate level of rigor for your class. But yeah, at this point, you sort of justify why the original thing can be split up into two separate parts, each of which you can apply the fundamental theorem of calculus to, right? This is basically where the negative sign comes in this expression. So at this point, you're basically just applying d dx to both portions. And yeah, let's maybe just look at applying d dx to this portion right here, because the derivative is a linear operator. Sorry, this should just be a subtraction sign. It looked like an equal sign earlier. Right, so if you apply the derivative to this first term, to see this maybe a little bit more clearly, you can use U substitution. I think this is just sort of one of your standard tricks, but this way it looks like du over d. Excuse me, I'm really tired today. So what happens here? Yeah, so if you apply, let's just write this out, yeah? So if you apply f of t dt, the idea is you really want to just, you'd really like to just have this u here instead of the h of x so that you know what to do. Yeah? But then instead of the ddx, you'd really rather hope to have a ddu instead. So I think the idea here, if I'm not mistaken, is to use the chain rule, right? Let's see how the chain rule would save us here. Gosh, I am feeling just miserable today. So yeah, let's see. I think this turns into d dx is basically the same thing as d du. And how do I want to express this? Yeah, if we want to call this entire thing like y, I think this just becomes like dy over dx is equal to dy over du times du over dx. And at this point, dy over du basically just looks like this thing. You take a derivative with respect to u, and the fundamental theorem of calculus pops it out nicely, which just turns into an f of u, right? But then you got to multiply the entire thing by du dx. And if u is equal to h of x, this just turns into an h prime of x. And then you can remember that u sort of just plugs in right here. So write this out sort of in your own explanation, in your own logic. But that should be the general gist. Yeah, sorry, this is not the most clean explanation, but I am feeling atrocious today. And yeah, hopefully that's enough to give you the gist. Basically, the entire deal here comes down to chain rule. So that dy over dx, ddx of the entire integral, f of t, dt from a to h of x. So we're basically saying this entire thing is y. So then this turns into dy du, which is basically just up here, which is just f of u in h prime of x. And then finally you substitute the un over here. So yeah, you can kind of see how we recover the desired term, right? This kind of turns into a u in here, and this thing right here is sort of the h prime of x we got down below. It's h prime of x. See that? Yeah, the entire thing turns out to just be chain rule. All right, enough blabbering from me. Let's keep going and make this a little bit more efficient. Okay, so the next part is we're saying that f is an odd function, and its antiderivative is f. Yeah, so that means that the integral of f of, let's call it f of t, dt from, I guess, a to x is equal to f of x. So we're wanting to prove, if f is odd, that means that f of minus t is equal to minus f of t. Right? That's just the definition of an odd function. Whereas even, the definition is f of minus x is equal to f of x. Basically, the minus sign just goes away. Right? An example of an odd function is sine, and an example of an even function is cosine. You can verify for that yourself if you wish. But the problem is that we want to show that f is even. So the way we do that is maybe we just start with an expression f of minus x, and we do some magic, some manipulations, and hopefully show that this is equal to f of x. Yeah? So that's the big outline. But I think that the way I was doing this was basically saying, all right, well, this is just equal to from a to minus x of f of t dt. And I just started playing around with this a little bit. I played around with this, and I'm sure there's probably a different way to do it. Maybe a cleaner way than I expressed. But what I did was I just sort of said, all right, well, let's just take the derivative of both sides here. And what did I get? I got that ddx of f of minus x is equal to f of minus x, right? Because this just sort of goes, this is the fundamental theorem calculus, it kind of goes right in there. But by chain rule, I would get an extra negative sign in front, right? Because the chain rule is being applied to the minus x right there. Okay. And because we have that f itself as an odd function, this means that the minus sign can just sort of pop right out and cancel out with that other minus sign. So this is just equal to f of x. And I said, well, okay, this is equal to, well, this is just equal to the ddx of f of positive x. And at this point, you can kind of see that, well, all right, we're getting something nice behavior here. We're getting that the derivative of x with respect to, f of minus x and f of x are, are equal to each other. And, well, what I did was I just sort of played around with this a little bit. Gosh, sorry, I'm feeling really not so great today. I think what I argued here was that, well, okay, if their derivatives of, f minus x and f of x are equal to each other, I think what I argued was just that if you like integrate both sides, you can kind of show that they got to be the same thing, right? Yeah, something like that. I don't know. Maybe this isn't the cleanest proof. Let me know if you find a better way to do this, but this is just what I got from thinking around for a couple of minutes. The general gist here is basically saying if f of minus x and f of x both have the same derivative, and you also, if they have the same derivative, you can tell a little bit about their parent function, right? That means their parent function can only differ by a constant. So then you kind of integrate it and kind of show that that constant has got to be 0. Yeah, I don't know. I'm a little bit worried that this is not the cleanest way, and maybe this is a little bit sloppy, but I think that makes some sense, right? Like if two different functions have kind of the same derivatives, right? Like their slope agrees at every point. That's kind of like saying, well, at worst, they look almost exactly the same, just maybe shifted up or down by a little bit, right? I think that's what that means. But then you also notice that choosing x to be 0 will let you figure out that that constant of integration has to go away. So maybe play around with that idea a little bit. Yeah. And maybe I should reapproach this problem a little bit because I really don't think that solution is very clean. But I think it kind of makes sense. Anyways, the next one, we're told that f is a continuous and positive function, right? So it's always greater than 0. So we're sort of being asked to prove that the integral from a to b of f of x dx is greater than 0. It kind of makes sense, right? It's sort of like saying if the slope is continuous and positive, show that the definite integral between 2 points is greater than 0. So let's try to figure out what that means, right? So visually, if excuse me. So what does that mean? So what would it be easier to graph? Yeah, maybe it'd be easier to graph the antiderivative, right? So like capital F being equal to the integral. But I think the idea here is, all right, so if it's slope, so big capital F's derivative is f, right? So little f is kind of the slope. So it's sort of like saying, okay, if your derivative is continuous and always positive, it kind of like means that you're always got to be increasing, right? Your slope's always got to be positive. And intuitively, what this means is basically saying that if the integral of f of x dx is greater than 0, I think that basically just means that I think that's basically just tantamount to saying that f has got to be increasing, right? It's basically saying that whatever this function value at b has got to be greater than the function's value at a, which kind of makes sense because its slope is positive. So intuitively, that shouldn't be too crazy. Intuitively, that should be pretty reasonable, I hope. But how do we show this? How do we show this? As part of your solution, state the theorems, if any, used in your proof. Yeah. Wow, I don't even remember what I came up with for this. So if f of t is equal to, I guess, from a to t of f of x dx, I guess this is kind of like saying, how do you express this? Right, proving that this thing is positive. I think you kind of have to assume that b is larger than a as well. But yeah, I'm trying to remember. If you know that, yeah. I mean, it's basically the exact same idea, right? So if you just take ddt of both sides, and you know that if you take ddt of both sides, then I guess you can call it this way: f prime of t is equal to f of t. So we are guaranteed by hypothesis that this is positive, so that this slope is, this slope is always positive. And if the slope is always positive, it's obviously increasing, right? So you can kind of, excuse me, because its slope is increasing, you can, well, what? Sorry, God, what am I saying? The slope is positive, so the function itself is increasing, right? So you know that, like I was saying over here, the function at b has got to be greater than at a. And what is this? This right here is basically just f of b minus f of a. So just argue that this is positive, and I think that's all you need to do, right? This is, like, this thing is just equal to f of b minus f of a. Yeah. Make that rigorous, play around with the idea, sort it out, but I think this should be reasonably clear. Oh god, he's really going very haphazardly. Oh gosh, I'm barely conscious right now. I'm so tired. But the show must go on for math. Anyways, for the function of f of x, for x being between 1 and 2, this is this problem seems kind of confusing at first, but it all works out quite nicely, right? So if this is the function 1 over x, the upper sums, okay, and our points of interest are 1, 2, and they also tell us to divide it into two subintervals of equal length, so 1.5 is also a point of interest. The upper sum is basically taking a rectangular approximation. So for this region between 1 to 1.5, it's basically taking the height to be the largest value in the range. And similarly for over here. So this is sort of an overestimate, right? So just add up the upper approximation of f using this particular partition is equal to just the area of these two triangles, which I'll let you figure out for yourself, right? You can just figure out whatever the height is from the function 1 over x, and the width of each rectangle is 0.5. Yeah. So what is this? This is height 1, and I think this is like 2/3 maybe. Yeah, figure out exactly for yourself. So this is whatever the value, a straight up genuine number or fraction. And then u of, I guess the lower bound, I'll draw it over here. The lower bound is a very similar idea. It's just using the lower approximation rather than the upper approximation. So if this is 1, 2/3, and a half, I think the idea is that 1, 1.5, and 2. So instead of using the largest approximation, it sort of uses the smallest value in whatever this interval as the rectangles. Yeah? And then at this point, you have to remember that we have a good friend from Calculus 1 called the Squeeze Theorem. Right, so just add up this value as you please. And essentially just have to remember that, okay, so if this is an under approximation of the true area under the curve, and this is an over approximation of the true area of the curve, here, I'll draw the real area. If the real area looks like this, right? This is undershooting it. This is overshooting it. So what you can say is that's like LF of P is less than or equal to like the true area, which is just the integral of 1 over x from 1 to 2, right? So these are genuine fractions that you calculated over here and over here. And this one over here, you can also, it just turns into a natural log, right? This expression over here looks, I think, ends up looking like natural log of 2. But you're going to compare this to the expressions given. And yeah, I think you should be able to massage that into the desired identity. So play around with that. Shouldn't be so bad. Yeah, the next one. All right. So I think we're told that f of x is increasing, invertible, and concave up, which means that the second derivative is positive. So this means that f double prime of x is greater than, is it greater than 0 or greater than or equal to 0? I forget which. You should probably figure that out exactly. But we're told that h is the inverse of f, and that h is such that h double prime of x is equal to minus f double prime of h of x divided by f prime of h of x cubed. So this problem looks really scary for just a moment, but like, I think it's actually not that bad. So basically you're asked to show that, you know, you basically want to show h is concave down, which, you know, the similar of but opposite of over here basically means that h double prime of x is less than or equal to 0. Or is it just less than? I forget. But the point is, you just look at this expression right here, right? They tell you what h double prime of x looks like. And you have this negative sign over here. And you know something about this numerator, right? We were told that the numerator, f double prime, is always greater than or equal to 0. And as for the denominator, well, f prime, we're told that f of x is increasing. So we know something about f prime, right? We know something about the sign of f prime. So just from that, you want to draw an overall conclusion about the sign of h double prime of x. So just think that through and see if you can show that h is concave down. Right? And of course, being less than or equal to 0 means that the sign is either negative or 0. Huh. Yeah. Okay. Logarithmic differentiation. Yeah. I don't think this is one that I can say too much on other than just looking up the process in your textbook and going through it. But like at a high level, logarithmic differentiation is really helpful in cases where you have like implicit differentiation as well as a bunch of exponents. But the general gist is that instead of trying to take the derivatives of the functions directly, like if you had x, y is equal to y of x, it's kind of like taking the taking the natural log of both sides, so that you can maybe bump these things down first, and then taking the derivative of both sides. It's, yeah, look it up. I probably can't explain this particular thing any better than the hundreds of explanations that exist, but the reason that this works kind of nicely is because sometimes you get really, really clean results when you do it this way, right? Sometimes you come up on situations where it's really, really nasty to take the derivative directly, but if you take the logarithm, things just nicely cancel out perfectly. I actually don't have an example off the top of my head, to be quite honest. I don't know, I'm stupidly tired. But like one recent example that's not logarithms, but really similar, comes from multivariable calculus. And if you have distance is equal to like x squared plus y squared, right? And you want to take like the derivative of distance with respect to like x or y, or just, yeah. Sometimes that's really, really nasty. So instead, a nice little trick in situations like these is to take the derivative with respect to d squared instead, because that just gets rid of the square root and things are so much prettier. Logarithmic differentiation is kind of similar, where taking the derivative with respect to the actual original thing is just terrible, but you take a logarithm and suddenly everything's so much prettier. Okay. So the next one is f of x is equal to ln of x minus 1. Find the first, second, fourth, and nth derivative. Yeah, I don't think I can say too much about this one, right? Just remember what the derivative of your natural log is, and remember how the power rule, the quotient rule works every time thereafter, and come up with a general formula. As well, use mathematical induction to prove the nth derivative of f is correct. Yeah, so I guess for a problem like this, I guess you should just really ought to look up what mathematical induction really is, right? Gosh, I hope you're all reasonably comfortable. But you prove a base case. The idea is if you want to prove something is true for... So if you want to prove something is true for all k, you prove it first for base case of like k is equal to 1 or 1. And then after that, the inductive step is given k is true, show that k implies k plus 1. And the way I like to visualize this is basically saying if you have a big number line and you want to prove something is true for every integer all the way, out to infinity, right? If this is k is equal to 1 and this is 2, basically you're manually proving that 1 is true, and I'm using a check mark to show that, it's good, it's true. And then if you can show that for an arbitrary k, if you can show that given an arbitrary k is true, that it implies k plus 1, right? If you can show that an implication step is true, this basically means that 1 implies 2, so now 2 is great, and now 2 implies 3, so 3 is great, and et cetera, et cetera, et cetera. So every single, you're basically proving the check mark manually for 1, and then proving the implication is true for k to k plus 1. And once you have those two things together, you have it true for everything. So basically, if you have some general formula for if you have some general formula of the kth derivative, show that leads to show that taking another derivative of that leads to f of k plus 1 is probably what you need to do. If this is equal to whatever, take the derivative of whatever and show that that's equal to your k plus 1 formula. Okay? All right, so the next one is basically a very silly... I don't know what I can say here other than just really check your rules. Remember, integration is kind of the opposite of derivatives. So they're kind of claiming that this is equal to 2 to the minus x plus 1 and minus x plus... They're claiming that this is the integral. So just go through and check to yourself. If you reverse the steps of integration, if you take the derivative, go back, it should bring you backwards. And I think you'll find that this is not true because they're using one of the wrong rules here. Right? This is one of the easiest ones to get mixed up for students who are learning calculus for the first time. But yeah, just definitely go double check and see which rule they're kind of abusing here. I don't want to give it away. I don't want to say it exactly. But yeah, just go through, look up your integration rules. All right. So for number 9, 2x over 1 plus x to the 4th. Yeah, this one... Yeah, it's a slight trick. Remember that at the bottom here almost looks like arctan, right? So I think, if I remember correctly, the integral of 1 plus x squared, or maybe let's call it u squared du, is equal to the arctan of u. Arctans, they're so crazy, man. Yeah, arctan. So the issue here is that this is x to the 4th. And we wanted to make it a u squared instead. So maybe try out the substitution for... excuse me. Maybe try out a substitution that will turn this x to the 4th into a u squared, and make sure to use the chain rule for the change of variable, as you should know how to do with u substitution, right? So if you choose u to be something in terms of x, you need to figure out what du is in terms of x and dx as well. So something in terms of x, something in terms of x and dx. Yeah, again, I don't want to give everything away, but it's okay. Number 10 is, on a standard xy plane, you have y is equal to e to the x, x is equal to 0, and y is equal to e squared. I really don't know that there's anything to really say about this problem. I think it's a pretty standard question to find the area. Um, I'm really surprised. Maybe I'm misreading this question, but it just feels like it's so deceivingly simple. Yeah, find the area, right? You can just figure out how to get the area from integration. But I think this is something that you've already should have been very comfortable with from the first homework set, right? Just finding the area is just doing the integral and then using the bottom as a bound and using the top as a bound, right? So if the bottom is e to the x and the top is e squared, yeah. Wait, am I doing something stupid? Oh no, what am I doing? What am I doing? Um, why did I choose the bounds? No, I think it should be the function instead, right? Yeah, something like that. And then just make sure to get the bounds right from 0 to whatever they meet up at, which is probably x is equal to 2. Yeah. Anyways, you can integrate with respect to x or y, doesn't matter. Just, well, x is integrating with respect to x is probably going to be easier. Yeah, sort that out. All right, let's talk about a real problem this time. Yeah, so this is something about water being put into a salt tank. So I guess the idea is that there's a fixed volume of water, but the amount of salt starts off with a ton of salt in the solution. And as you add in pure water and drain the water, the salt kind of gets diluted, right? It doesn't go to zero, or like it's not going to immediately go to zero, right? Because you're sort of diluting it and then draining it. Yeah. It's kind of like if you were diluting down like a soda or something, right? You dilute it and then pour some out, dilute it and pour some out. There's still going to be a little bit of fizziness, right? It's just going to be reduced. It's not going to be quite zero. But okay, the idea is this is expressed by, so if the amount of salt is S, V is the volume, which I think is just constant. And W is the amount of water that gets poured in, right? So W is the total amount of water you've poured in since the start. And as you might expect, the longer you've poured in W and drained it out as well, the lower the concentration of the salt ought to be, right? S should go down. So the idea is they represent this as a differential equation, a very simple differential equation. ds is equal to this, right? And the key to differential equations like this is when you see a ds and an s, and you can see that it's you can isolate all the s's on one side and the w's on the other. This is called a separable differential equation. And these are like, baby's first differential equations. These are the easiest to solve. And the way you do it is, of course, just integrating. And you can see that ds over s is, well, a very particular type of integral, right? It's a, well, we've used them even in this homework set before, just slightly obscured. Gosh, I'm so tired. Yeah, but this should give you some sort of function in terms of s. You can isolate s, and then you'd also don't forget your constant of integration as well, right? But you're going to have to plug in initial conditions to find the constant of integration, right? And I think its initial conditions that they gave you was s naught, right? When t is equal to 0, s is equal to s naught. So like s of t is equal to 0 is equal to s naught. And this should clue you in as to what this should help you figure out what exactly c is going to be. Yeah, I think that's probably all I should say about that one. But what is it asking? Find the amount of water that must be added into the tank to eliminate 25% of the initial amount of salt. Yeah, I mean, I did go through and solve this one. I just think it's, it'd be, I don't want to give spoilers about how everything is done. But the point is, okay, maybe I'll skip ahead a few steps and sort of talk about things later. But I'd expect this to look like, after solving a couple steps, e to the minus, I think, w over v with some constant out in front, maybe some different, let's call it some, I don't know, some constant a out in front. being multiplied by it. I think the idea here is that excuse me, I'm very tired. My notes go. Yeah, I mean, I feel like you could probably figure it out for yourselves at this point. Let's do it in my head. Oh yeah. Okay, so basically, this is going to be some expression of S naught, right? And you can basically put, divide through by it, to represent the fraction. So if 25% of the salt has been eliminated, the fraction probably is going to look like 0.75. And at that point, you basically just have to solve for whatever value of W is going to give you 0.75, something like that. All right. Yeah, that's probably all I should say. Okay, so if you have something like x minus 1 plus e to the x minus 4. So again, if we want to prove that there exists a c that's in 1 to 4, such that f of c is equal to 0, I'm hoping that your experience from last semester screams that there's one particular theorem you should use, right? It's a good exercise just to think to yourself out loud. What is this screaming in terms of what you should use, right? Remember the audience, pause and think of it, because I really feel like you should think of it yourself, right? Okay, now pause and come back to the video. But once you've come back, here it is. It's IVT, Intermediate Value Theorem. So what's happening here? 1 and 4 are sort of where these functions have vertical asymptotes, right? I think what happens is that near 1, near 1 approaching from the right. Okay, so what does this look like? 1 and 4. So around this area, just to the right of 1. So like around this area. Well, if it's just a tiny bit more than 1, then x minus 1 is positive and x minus 4 is negative. So this looks to me like it's going to diverge down to negative infinity somewhere, right? And then, so I'm going to draw that vertical asymptote. And similarly for 4. And then for 4, wait a minute, did I do this one right? Oh, I'm so stupidly tired. Wait a minute, is it intermediate value theorem? Maybe I misspoke on that one. Let me think about this for a second. Because the issue is that the denominator is going to be negative in both situations, right? So yeah, wait a minute. Maybe this isn't so obvious. All right, let me rethink this. Am I stupid? Oh, no, I'm stupid. Yeah, no, I had worked out that I had thought through this earlier. I don't know why I said that this was negative. No, so let's think about this carefully again, right? Um, for both, any value between 1 to 4, this value over here is going to be positive, and this value over here is going to be negative. But what's going to be different is the relative sizes, right? Close to, oh God, what am I doing? That was so silly of me. Close to x is equal to 1 from the right side, this thing becomes humongous, right? This thing becomes a massive value. I think I got my signs wrong earlier. So this looks like, something near, going up to positive infinity. Whereas over here, once it gets closer to -4, this is the term that, when it gets closer to 4, this is the term that blows up in magnitude, and it's got a negative sign. So it looks sort of like that, right? And it's pretty clear that it's going to be continuous on this interval. So you just basically choose some point near 1, choose some point near 4, and invoke IVT, and argue the rest yourself. Yeah, okay. Gosh, I'm all over the place. I looked through this last night, and I made all the arguments myself. It seemed fine. I just I'm very out of it today. All right, does that cover everything? Yeah, I just feel like I was a little bit shaky in my explanation of maybe number 2, where we were talking about when f is odd and its antiderivative capital F is even. I mean, I think our discussion of it was sufficient. But let's take a look again. Yeah, right. If you kind of show that the derivative with respect to x is nice for both, same thing for both, you kind of, well, everything kind of takes care of itself. Yeah, I just want to know if there's a different way to think about this that's maybe a little bit more clean. But fundamentally, I think that the minus sign to sort of, the minus sign kind of gets plugged in there because of fundamental theorem of calculus, but chain rule pops out another minus sign, and that's sort of where the odd function kind of, kills its own negative signs. Yeah. Anyways, I think that should do it for today.